All right, in this video we're going to look at inductive reactance. And you might wonder why this series on reactance and impedance and so forth. There are some questions on the extra class license that deal with reactance. So you're going to need to know them. And they're good to know anyway. They have practical application, particularly when we're talking about impedance matching. I already mentioned that in the previous video, that impedance is a combination of the reactance and the resistance in a particular circuit. Okay, let's look closer here at inductive reactance and see if we can puzzle out some of the stuff, what the relationship is. So let's start with an alternating current source, and let's run it through a coil, which is an inductor. And this, of course, is our frequency source, alternating current. And this is our inductor. And so we're looking at a situation like this, where we have a sine wave, and the frequency is the time it takes to get from the beginning of the cycle to the end of the cycle. And this is the positive half, this is the negative half. Why is that important? Well, we know that when current passes through a wire, DC or AC, it builds up a magnetic field around that wire. And here we have several coils of wire all next to each other. So there is a direct relationship between how much resistance or reactance, remember reactance is the resistance to a change in AC current, is to how it resists that. It takes a finite amount of time for the field to build up in this coil. And notice that as we go through our cycle, it's building up this way, it gets to the top, then it starts collapsing, it goes to zero, and then it starts building the opposite direction until it gets back to zero again. Okay. It's probably not difficult to visualize then that as the frequency goes up, the faster this has to build up and tear down that field. Well, at higher frequencies, because it is a finite amount of time to do that, this reactance goes up. So X sub L also goes up, and it goes up in proportion to what the frequency goes up. So that's how these two things are related. As frequency increases, so does the reactance of this coil. So let's look at the formula. X is the letter used for reactance, and we'll put a subscript of L, because we use the same letter X for reactance for a capacitor, but we have C. Okay. The first thing we encounter in the formula is 2 pi times the frequency times the value of inductance. Well, where does this 2 pi f come from? What is that about? Well, recall from, if you're not familiar with radians, review my video on, I have a video where I talk about radians and degrees and converting between them and whatever. This is one of those cases where instead of having this cycle measured out in degrees, we have it measured out in radians. And one full cycle takes 2 pi radians. And so we're simply multiplying one whole cycle times how many times that cycle occurs. That's really what this statement means. And I should mention that since this relationship happens a lot in physics, and particularly in electronics, some of those people like to use a shorthand for it, so they'll use the lowercase Greek letter omega. You're familiar with the upper. That's the ohm sign. This is the lowercase. Omega stands for 2 pi f. I'm not crazy about using that because it's an abstraction of another abstraction. After a while, it gets too many abstractions to remember. And why do we use it? We get x sub l is equal to omega l. Okay, it's a faster way to write it, but so what? I still have to decode it at some point. Don't be so lazy. Write it out. That's what I say to those guys. And they probably have words that they would say to me too. All right, but that's okay. Anyway, so this is the relationship. And since one is directly equal to the other, this is where we get the idea that they're proportional, meaning that as one goes up, so does the other. All right, let's do a calculation. Let's say we have a coil that's rated at 82 millihenries, and our frequency is 2.65 megahertz. Let's plug those into our formula here and calculate what the reactance is. Remember, reactance is the opposition to the change in the flow of current. All right. So let's write this out. X sub L then is equal to 2 pi times our frequency. You don't need parentheses to enter it. I'm just trying to separate our players up here. So our frequency then is 2.65 times 10, it's in megahertz to the 6th power, times our inductance. Now this is milli. That's times 10 to the negative 3. So we have 82 times 10 to the negative 3. And when we do this calculation, that should tell us what the opposition is in ohms of reactance to the change here in the current flow. So let's do 2 times, and we'll use our pi key here, times our frequency, which is 2.65 times 10 to the 6th power, times 82 times 10 to the negative 3 power. Now when you enter this in, don't use the subtraction key. If you have a scientific calculator, undoubtedly it has a change sign key. Most of the current calculators use this negative between two parentheses. Sometimes you see it as a plus minus. Okay, let's press enter, and we get a value then of 1365336, and we won't worry about the decimal point. So that's 1,365,336 ohms, or just rounding it up, that's approximately equal to 1.4 megohms. That's a considerable amount of resistance. Okay, great. So there's a calculation then, finding out what the inductive reactance is at a particular frequency. And as frequency changes, that's directly proportional to the change in this. If frequency were going down, then the inductance goes down. All right. Next, we will look at capacitive reactance, and we'll see that we have an inverse relationship there. Okay. More about that when we get to that video. See you then.